Previously, we have written down the wave equation for electric field of light, but that was in one dimension. In reality, light is a three-dimensional electromagnetic wave. So we have to generalize that one-dimensional wave equation to a three-dimensional wave equation. So let's begin. Now, we know that light is an electromagnetic wave. So it has both an electric field and a magnetic field, which are three-dimensional in nature, and it can propagate in any direction. You can visualize the magnetic field and the electric field of light by using this diagram. If light is propagating in this direction, then both the electric field and the magnetic field is actually perpendicular to the direction of the propagation of light. And this electric field and magnetic field are also perpendicular to each other, as you can see from this diagram. So, light is a three-dimensional vector field. That is, it assigns a three-dimensional vector to each point in the three-dimensional space. So, the wave equation for the electric field or the magnetic field of light will need three-dimensional treatment. Now, in order to explain the different properties of a three-dimensional vector field, we need to introduce a three-dimensional operator which we call the del operator. It is equal to, as you can see, partial derivatives with respect to x, y, and z. Well, this is a vector operator, and the unit vectors are built into this notation. This delta operator is actually equal to I unit vector times ddx plus j ddy plus k ddz. Now, when this delta operator works on a scalar function, we get the gradient of that scalar function. So, the gradient of the scalar function f is defined to be this quantity. And as you can see, this is a vector quantity, so it has a direction, right? This gradient points in the direction of the steepest ascent or the steepest rise. Now, if we do a dot product of the del operator and a vector field, we get something that we call the divergence of that vector field. So this quantity tells us if the field is diverging or converging and in what amount. So this is a figure with non-zero divergence. The divergence of a vector field is non-zero if there are sources or sink in that field. Now, for our purpose, we need another operator which is known as the Laplacian operator. This is nothing but the del operator dotted with itself, which we denote by delta square. So, when the Laplacian acts on a scalar function f, what we do is, first we take the gradient of the scalar function and then we dot it with the delta operator. That is, we find out the divergence of the gradient. That's how we get to this result. Now, what happens when we apply the Laplacian to a vector function? Well, it still gives us this result, but for each component of that vector function. Now, what does this Laplacian really mean? Well, it tells us about the curvature of the vector function. Now, we know that light wave can propagate in any direction in space, which is three-dimensional in nature. So for that, we need a three-dimensional wave equation. And to generalize the one-dimensional wave equation to three-dimensional wave equation, we must replace the one-dimensional space derivative, which was ddx, with three-dimensional space derivative, which we call delta. So the wave equation for electric fields in three dimensions takes this form, where we have replaced the partial derivative with respect to x with this delta operator. And if we expand this Laplacian in Cartesian coordinates, it would look like this. Now, the solution of this three-dimensional wave equation will also have some three-dimensional quantities here. Previously, for one dimensions, it was just the real part of E naught times e to the power ikx minus omega t. Now, we have to replace that kx with this dot product between k vector and r vector. So this k vector has three components. Also this r vector. This k vector dot r vector in Cartesian coordinate system will look like this. And the magnitude squared of this k vector is equal to kx squared plus ky squared plus kz squared. So this electric field is a function of x, y, z and t. Now, one thing about this notation is that here we have taken out the initial phase, which we would have called theta, inside this amplitude, which made this amplitude complex. But the electric field of light wave can point in any direction in space. So it is a vector quantity. So the three-dimensional wave equation for light wave electric field is actually a vector equation. So we have to write the electric field as vector in the wave equation. Then its solution is also a vector quantity, where the amplitude E naught has three components: E naught x, E naught y and E naught z in Cartesian coordinate system. But remember that this E naught is also a complex number. So its x, y and z components will be complex too. So the complex vector amplitude has 6 numbers that must be specified to completely determine this E naught vector.